Hi guys. Okay, so today we're going to talk about asymptotes. We're going to make connections between the equations of a rational function and its graph. And we're going to focus particularly on asymptotic behavior, but also a couple other things. So the first thing I want to look at are non-canceling factors in the denominator. So we're going to focus on non-canceling factors in the denominator. So we're going to consider this function g of x below, and based on the equation of the function, explain why the function graph below has a vertical asymptote at x equals -3. So here's the function g of x, and they were even nice enough, and they factored it for us. So you'll notice that the common factor 2x plus 1 and 2x plus 1 would cancel out. Now that leaves a non-canceling factor in the denominator of x plus 3. Now, if we set x plus 3 equals to 0, and we solve, we have x equals -3. And notice, that's exactly where we had the vertical asymptote. So when the equation has a factor in the denominator that does not cancel out, then the graph has a vertical asymptote at the x value that makes that factor equal 0. There you go. That's how you find out what vertical asymptotes are going to be. You factor, you simplify, you take what remains in the denominator and set it equal to 0. Now let's take a look at the canceling factors that are in both the numerator and denominator. So again, we have that same function g of x, and we have the same graph. But this time, we're going to focus on the canceling factor 2x plus 1. Now, if I set 2x plus 1 equal to 0, that means 2x would equal -1, or x equals -1/2. Well, what's happening on our graph when x is -1/2? Well, look at this. That's where there's a hole. So when an equation has a factor in the numerator and denominator that does cancel out, then the graph has a hole at the x value that makes the factor equal to 0. Now there's a little more to having a hole though, because a hole has coordinates. It has an x and a y value. So now we know where the x value is, but to find the height of the hole, which is the y value, we plug the x value into the simplified function. So for this particular function, once we simplified it, we are left with -x minus 2 over x plus 3. So we're going to take this -x minus 2 over x plus 3, and we're going to let, where did we say the hole was? At x equals -1/2. So the negation of a -1/2 is a +1/2, minus 2 over -1/2 plus 3. Now 1/2 minus 2, that's -3/2 over -1/2 plus 3, that's 5/2. So we have -3/2 times 2/5, that's -3/5. That is the y value. So now we know that our hole has the coordinates -1/2, -3/5. Okay, so to find the coordinates of a hole, you factor the function, simplify. The factor that canceled out, find the root of that, that's your x value. Take that x value, plug it into the simplified function, and you'll find the matching y value, which is the height of your hole. Now let's talk about the non-canceling factors in the numerator. So let's take a look at the function f of x and the function g of x. I've given you the graphs, and I've given you the functions. Now we need to factor them. So f of x, if I have 2x squared plus 7x plus 6, 2 times 6 is 12. So I need two numbers that multiply to a 12 and add to 7. That would be a 4x and a 3, right? So we'd have 2x squared plus 4x plus 3x plus the 6. And if we group that, we have a common 2x, which will leave us with x plus 2. Over here, we have a common 3, which leaves us with an x plus 2. Now we have that common x plus 2, and when we factor that out, we're left with 2x plus 3. So our numerator is x plus 2 times 2x plus 3 all over. Now in the bottom, we have a trinomial. They have to multiply to 6 and add to 5. That's going to be an x plus 2 times an x plus 3. Now the x plus 2's are going to cancel out. So now which factor is in the numerator that does not cancel out? So the factor that's left in the numerator is 2x plus 3. Now, what value of x makes that 0? Well, if I set 2x plus 3 equal to 0, 2x equals negative 3, or x equals negative 3 halves. Now look on the graph. What's happening when x is negative 3 halves? Which remember is x equals negative 1 1/2. There it is. That's an x-intercept or a root. So we have an x-intercept or a root or a 0. Let's see if the same thing happens with g of x. So let's look at g of x. If we factor g of x, we have an x and an x. We need two numbers that multiply to 3 and add to 4. That's 1 and 3. In the bottom, we need an x and an x. We need two numbers that multiply to negative 3 and add to 2. That's a negative 1 and a positive 3. The x plus 3's cancel. Now, what factor does not cancel out in the numerator? That's x plus 1. Now, if we let x plus 1 equal 0, that means x equals negative 1. So let's look at the graph of g. When x is negative 1, there it is. It's crossing the x-axis. There's our root. So again, when an equation has a factor in the numerator that does not cancel out, then the graph has an x-intercept or a root or a 0, whatever you want to call it, at the x value that makes the factor equal to 0. Okay, next we want to talk about the shape of a graph near the origin. Now remember, when we're near the origin, those are really small x values. The x values get really tiny, right? X could be 0.0000000000001, really close to 0. So now what I want you to do is on your calculator, graph f of x equals x cubed minus 5x. Okay, so here we are. We're going to graph x raised to the third, get out of my exponent, minus 5x, and we hit enter. Here's our graph. Okay, we're back. So our graph looked something like this, right? And we have no numbers on our graph. We just need the shape. Now, go back to your calculator and zoom in on the origin. I want to know what's happening near the origin because that's when the x values are getting close to the origin. What happens now? I want you to zoom in several times and let's see what happens. Okay, so now we're going to zoom in. So we go to Menu, Window Zoom, Zoom in, and I'm going to click right on the origin. I'm zooming in and zooming in and zooming in. And what does that look like? Okay, so we saw that our graph started to look like this line. What line is this? Go back to the function. If the x values are headed to 0, when I cube those values, they're going to get close to 0 faster then 5 times the number. If you think of 0.0001 and you cube that, that's a much tinier number than 0.0001 times 5, right? So that highest power of x gets insignificant. It shrinks much faster. And all that's left is y equals negative 5x. And notice that's the line we saw when we zoomed in. Okay, let's take this function. Now I want you to go to your calculator and graph g of x is x cubed minus 5x squared. Okay, so now let's put in a new graph page. And this time we're going to graph x raised to the third, get out of the exponent, minus 5x squared, and hit enter. I'm going to slide this. Oh, maybe we're just going to change this. Let's try negative 20. How does that work? There we go. Now we have a graph where we can see the maxes and the mins. Okay, so our graph looks something like this. Okay, so we have a cubic. Now, go back to your calculator and zoom in on the origin several times. What happens? Now we're going to zoom in. So menu, window, zoom in, and we're going to zoom in on the origin. Oh, look at what that looks like. Wonder what that is. Okay, it starts to look like this, doesn't it? That looks like a parabola. What parabola is that? Look at this function again. The x cubes are going to get to 0 faster than the 5x squareds, or the negative 5x squareds. So this starts to look like the parabola negative 5x squared. So as we're headed towards the origin, the highest power of x becomes insignificant and disappears, and what's left in the equation becomes what the graph looks like near the origin. The next thing we want to look at is the existence of horizontal asymptotes. Okay, so we're going to compare the degree of the numerator and the denominator. So we have this function f of x, which is x to the first minus 3 over x squared minus x minus 6. So the degree of the top is 1 and the degree of the bottom is 2. And notice there's a horizontal asymptote here at a height of y equals 0, right at the x-axis. Let's look at the other f of x. F of x is x to the first plus 2 over x squared plus 5x plus 6. And again, this graph also has a horizontal asymptote at y equals 0. Now, what do you notice about the degree of the numerator compared to the degree of the denominator? The degree of the numerator is smaller than the degree of the denominator, right? And both of these have a horizontal asymptote at y equals 0. Now, why does that make sense? Because if the degree of the bottom is bigger, it means the bottom of the fraction is getting bigger faster than the top. For instance, 1 over 10, 2 over 100, 3 over 1,000, 4 over 10,000. Now, both the top and the bottom are getting bigger, but the bottom is getting bigger faster. And what's happening to the values of the fractions? 1 over 10, 2 over 100, 3 over 1,000, 4 over 10,000, 5 over 100,000. Those values are getting smaller and smaller and smaller and closer to 0. And that's why there's a horizontal asymptote at y equals 0. Now let's look at these two functions, g of x. So here, g of x is x squared plus 3x plus 2 over x minus 1. I don't see a horizontal asymptote on this graph. I see a vertical asymptote. I even see this dotted slant line, but I do not see a horizontal asymptote. Let's look at the other one, g of x is x squared minus 5x minus 6 over 2x to the first. Again, the degree of my numerator is bigger than the degree of my denominator, and we seem to have no horizontal asymptote. Now let's think about this. If the degree of the top gets bigger faster than the bottom, then the top is getting bigger. 10 over 1, 100 over 2, 1,000 over 3, 10,000 over 4. Those fractions are getting bigger and bigger. They're increasing without bound. They're heading to positive infinity. Now, if they're negative, it might be negative 10 over 1, negative 100 over 2, negative 1. Now they're decreasing without bound and headed towards negative infinity. But in either case, there's no horizontal asymptote. Now, let's look at h of x. So h of x, we have two of them. We have 2x squared plus 7x plus 6 over x squared plus 5x plus 6. And we have h of x is negative 2x squared minus 5x minus 2 over 2x squared minus 7x plus 3. What do you notice about the degree of the numerator compared to the degree of the denominator? It's 2 and 2. They're the same. Over here, it's 2 and 2. They're the same. So the degree of the numerator equals the degree of the denominator. Now, let's look at the first function on the left. That's this one over here. Where is the horizontal asymptote? Horizontal asymptote is right here, and that has a height at 2. So it's y equals 2. Now, it's asking us what is the value of y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator of h of x. So if I look, my leading coefficient is the constant in front of the x squared over the constant in front of the x squared. That would be y equals 2 over 1, or just y equals 2. That's familiar. Okay, let's look at the function on the right. Where is our horizontal asymptote? Here it is. That has a height of negative 1. Now let's do the same trick with the leading coefficients. In the top, the leading coefficient is negative 2, and in the bottom, the leading coefficient is positive 2. What's negative 2 divided by 2? There it is. It's y equals 1. All right, so let's sum up what we just learned about horizontal asymptotes for rational functions. If the degree of the denominator is greater than the degree of the numerator, so the bottom gets bigger faster, 1 over 10, 2 over 100, 3 over 1,000, that means that our horizontal asymptote is y equals 0. If the degree of the numerator is bigger than the degree of the denominator, 10 over 1, 100 over 2, 1,000 over 3, there is no horizontal asymptote. That graph is either increasing or decreasing without bound. And the last possibility is if the degree of the numerator equals the degree of the denominator, so they're the same, that means that the horizontal asymptote is y equals the leading coefficient of the numerator over the leading coefficient of the denominator. Do you know there's another type of asymptote? That would be called a slant asymptote. They're also sometimes called oblique asymptotes. and I'm going to tell you why in a minute. So notice that the graph below has a slant asymptote because the line is slanted. Here it is. Doot, 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 doot. This will always occur when the degree of the numerator is exactly 1 greater than the degree of the denominator. That's important. The degree of the numerator is exactly 1 more than the degree of the denominator. So let's say degree of numerator equals 1 plus. Now, from the graph, what is the equation of the slant asymptote? So it should be in the form y equals ax plus b or y equals mx plus b. If we look at this line, the slope of this line, or actually the y-intercept, we can see that y-intercept, there it is, right there at 4. The y-intercept is 4. What's the slope of that line? It looks to me like it's going up 1 and over 1, up 1 and over 1, up 1 and over 1. So that slope is 1. So the line is y equals mx plus b. So the equation of the slant asymptote is y equals x plus 4. Now, the equation of the function graph to the right is g of x equals x squared plus 3x plus 2 over x minus 1. We're going to do synthetic division now. So if we look at the denominator x minus 1, the root of x minus 1 is 1, so that goes in our box. Now the numerator is a quadratic. We have 1x squared, we have 3x's, and our constant is 2. And we're going to do synthetic division, so we bring down the 1. 1 times 1 is 1. Now we add, 3 plus 1 is 4. 1 times 4 is 4. Now we add, 2 plus 4 is 6. Now if we look at this, y equals, now we had a quadratic, so these are the coefficients on a linear, 1x plus 4, and the remainder is 6. Or we usually write that y equals x plus 4 plus 6 over x minus 1. However, if you just look and you ignore the remainder, here is your slant asymptote. So your slant asymptote is y equals the quotient when you do synthetic division, and you ignore the remainder. Let's see if this works again for this one. Now from the graph, what's the equation of the slant asymptote? So now this time, where is our slant asymptote crossing the y-axis? There it is at -1. So our y-intercept is -1. What's the slope? We're going up 1, and I have to go over 2 to find the next point. Up 1 over 2. So our slope is 1/2, which means our line is 1/2 times x plus a -1. There's the equation of our slant asymptote. Now, h of x is x squared minus x plus 1 over 2x plus 2. And we want to do synthetic division, but there's a problem. That denominator does not have a leading coefficient of 1. So we have to factor out the 2. That'll leave us with x plus 1. That's not a problem, but we also need to factor out a 2 in the top. That's going to leave us with x squared over 2 minus x over 2 plus 1 over 2 in the top. Okay? I know you're nervous because you see the fractions. Trust me, it's not that bad. Let's do synthetic division. The root of x plus, oh, and we forgot to show this. The 2's cancel out. Yay. Now the root of the denominator, x plus 1, is -1. Now our coefficients on the x squared are now 1/2. The coefficients on the x are -1/2. And the constant is +1/2. We bring down the 1/2. -1 times 1/2 is -1/2. Now if I add -1/2 and -1/2, I get -1. -1 times -1 is +1. I add 1/2 and 1, I get 3/2. I box that because it's my remainder. So we get y equals 1/2 x minus 1, and then remember, our remainder is 3/2 over that x plus 1, but we ignore it and y equals the quotient is our slant asymptote. So the slant asymptote, to find the equation of the slant asymptote, we do synthetic division, and ignore the remainder. Okay, let's try a couple examples of just finding the slant asymptote. First, we have to decide if there exists a slant asymptote. Now remember, there's only a slant asymptote if the degree of the numerator equals the degree of the denominator plus 1. So if we look at f of x here, we have 3 as the degree of the numerator and 1 is the degree of the denominator. This is not going to have a slant asymptote because the degree of the numerator is 2 more than the degree of the denominator. Now I want you to pause for a minute here. I want you to think about a horizontal asymptote though. If the degree of the top is 3 and the degree of the bottom is 1, the top gets bigger faster. There's going to be no horizontal asymptote either, okay? So it's possible to not have a horizontal and to not have a slant. But can you have a slant and a horizontal? No, because if the degree of the numerator is bigger at all, there is no horizontal asymptote. And in order for there to be a slant asymptote, the degree of the top has to be bigger. So if you have a slant, there is no horizontal asymptote. If you have a horizontal asymptote, there is no slant asymptote. You can't have both. Okay, let's look at g of x. Here, the degree of the top is 2 and the degree of the bottom is 1. This is the case that we want. The degree of the top is 1 more than the bottom. So we're going to do synthetic division. X plus 4 is in the bottom, so that root is -4. Now we take the coefficients of the top. I have 1/2 x squared, I have 5 x's, and I have a constant of -4. Bring down the 1/2. Now we multiply. -4 times 1/2 is -2. Add them, I get 3. -4 times 3 is -12. Now, in all honesty, I don't even have to finish this up and say -16 because I don't care about the remainder. Once I get to the step before the remainder, I'm done. This is my slant asymptote, because remember, I'm not looking for the answer to division. I'm looking for the equation of my slant asymptote. And we ignore the remainder. All right, last example. We have another g of x. We have the degree of the top is 2. The degree of the bottom is 1. All right, so we will have a slant asymptote because the degree of the top is exactly 1 more than the degree of the bottom. However, before we can do our division, we need to factor out that leading coefficient in the bottom, which is 2. If I factor that out, I'm going to be left with x plus 2. But if I factor it out of the bottom, I have to factor it out of the top. That will leave me with 1/2 x squared minus 5/2 x minus 3. Now my 2's will cancel out. That'll make us happy. Synthetic division. In the bottom, we have x plus 2. The root of that is -2. In the top, I have 1/2 x squared. I have -5/2 x's, and my constant is -3. I'm going to bring down the 1/2. -2 times 1/2 is -1. -5/2 and a -1 is -7/2. Now, if I multiply -2 times -7/2, I'm going to get 7. And again, I don't even have to finish this up and say that the sum is 4 because I already know that my slant asymptote is y equals 1/2 x minus the 7/2. We do not need the remainder. when we're looking for our slant asymptote. Okay guys, so we've learned a lot tonight. The slant asymptote, if the degree of the top is bigger than the degree of the denominator by 1, we do synthetic division and ignore the remainder. Horizontal asymptotes, we look at the degree of the top and the degree of the bottom. If the degree of the bottom is bigger than the bottom gets bigger faster than the top, and the horizontal asymptote is y equals 0. If the degree of the top is bigger, the top of the fraction gets bigger faster than the bottom, there is no horizontal asymptote. If the degree of the top is the same as the degree of the bottom, then your horizontal asymptote is y equals the leading coefficient of the top over the leading coefficient of the bottom. We also learned that if we take a rational function and we factor it, there are several things we can find. So we factor. If we factor, we look at the terms that cancel. The term that cancels, if we find the root of that, that will give us the x-coordinate of any wholes. Now to find the height of the whole, we take that x value and we plug it into the simplified function. Also looking at this simplified function, if we look at what's left in the denominator and set it equal to 0, that will tell us where our function has vertical asymptotes. If we take a look at what's left in the top of our function and set it equal to 0, that will tell us where the x-intercepts or the roots of our rational function are. Okay guys, we learned a lot today. We will practice in class. See you then. Have a good one.